Костиков нет почему-то, вроде бы у него занятия должны были уже кончиться. Может, правда, на каникулы уехал. Okay, just 1 minute left, so I announce our last session in this year. Our speaker is Mikhail Markov, and you see the title, Boundary Calculus for Gauge Fields on Asymptotically Anti-de Sitter Spaces. And I think you can begin. Please start.
Okay. Thank you. Thank you for this opportunity. And this talk will be based on our joint work with Maxim Grigoriev. And the idea was that he, 3 weeks ago here, he described the main ideas of this work, more like ideology, and I will give more technical details. But also, of course, I will recall ideology and these things. So what we are going to study? We are going to study gravity on, well, we are going to study asymptotically AdS gravity and boundary structure induced by gravity on the boundary. And we will do it in some formalism called GHPD formalism, and I will recall some basics of this formalism. And then we'll consider also some gauge fields living on this background, on background of gravity. So we are interested in theories defined on manifolds with boundaries, in particular asymptotic ones, and gauge field theories are especially interesting in this context because many strange things might happen on a boundary when we're talking about gauge field theory. And in the context of gravity, general relativity, it's a long story. I mean, papers cited here are like, some of them are from 60s, but in last years, there are new, a lot of people interested in it. And if cosmological constant is non-zero, asymptotic boundary for gravity is a conformal manifold, and conformal geometry methods are also quite useful there. But when we're talking about gauge field theories in general, we know that it's useful to work with some version of Batalin-Volkovitsky formalism. And if you want to take locality into account, usually we work with a reformulation of BV in terms of jet bundles. But for gauge field theory, jet bundle structure is a bit too rigid, and there exists some more flexible object called gauge PD. And the main feature of this object, I mean, not the main, but one of the features of this object is that it behaves well when restricted to some submanifold boundary or something. And today we'll talk only about boundaries. So idea of the talk is to illustrate this formalism and its applications to boundary structure of gravity and fields on its background. The main definition that we will need is a definition of Q-manifold. Q-manifold is a Z-graded supermanifold equipped with an important vector field of degree 1. And basically it means that Z-graded means that algebra of functions on our manifold is Z-graded, and super means that it's also Z2 graded. And in this talk, always Z2 grading is just Z grading module 2. And I can give simplest example of this Q-manifold. Suppose we have some smooth manifold, and usually today I'll work in coordinates. Suppose we have some smooth manifold, we can construct something called shifted tangent bundle of X. In coordinate, it just means that we are taking tangent bundle to our X, and then we shift parity of the fiber. So we are declaring that now, in coordinates, we're declaring that now our fiber coordinates are anti-commuting. And it's canonically equipped with the following vector field, dx. You can just construct it contracting thetas with partial derivative in x's. And by construction, it's nilpotent because partial derivatives are commuting and thetas are anti-commuting. And easy to see that the complex of functions on T1x equipped with this dx is isomorphic to the derived complex of forms, differential forms on our original manifold X. And in this talk, I'll usually call this Z degree as Gauss degree. Yeah. So now I'm ready to define gauge PD. Gauge PD is a bundle in this category, which means that our total space is a Q-manifold, our base space is a Q-manifold, and we ask projection to be compatible with these two Q structures. But also we ask base space to be this particular Q-manifold constructed from some X, this shifted tangent bundle. And we interpret X as space of dependent variables or as a space-time in physics. And we defined PD, and we can define what is the solution of this PD. Solutions are sections of this bundle such that they are compatible with 2Q structures. And also we can define the infinitesimal gauge transformation of some given section using some Gauss degree -1 vector field on space, on the gauge PD. And why it's gauge PD? It encode the gauge field theory at the level of equations of motion. And of course, if you want to add some additional, if you want to talk about Lagrange instruction, for example, you can do it. But this talk will be about level of equations of motion only. Okay. And to connect it with what people know, I'll give PD example of gauge PD. Suppose we have some non-graded bundle E over X. Using canonical projection of shifted tangent bundle to X, we can define the pullback bundle. The following pullback bundle, we are just taking infinite jet bundle of our original bundle, and then pull it back to T1, to the bundle over T1X. And by this, in coordinates, it simply means that we are adding theta coordinates to our original jet bundle. And we can define Q structures there simply by contracting thetas with total derivative on jets. And because total derivatives are commuting, Q is nilpotent. It's the same argument as for this superversion of the RAM complex. And then this bundle is a gauge PD. But, we can check, I gave a definition of solution of gauge PD. In this concrete example, it will be the following condition on sections, and it's just a usual condition that total derivative is left of partial derivative. And gauge transformations are trivial. And but this is, I described jet bundle in this language, and if we want to consider some non-trivial PD, on-shell PD, we need to take some sufficiently regular function G on the total space, and we can define ideal generated by all of prolongations of G. And by construction, Q is tangent to the zero locus of this ideal, and then we can this zero locus of this ideal will give us gauge PD that describe non-trivial PD. But in this talk, we'll work with kind of specific gauge field theories, because as I said, we want to consider gravity and fields on its background. And this system are diffeomorphism invariant. And it's known that for diffeomorphism invariant systems, gauge PD is locally trivial as a Q bundle. So it's, of course, we always assume that it's locally trivial just as a bundle. But local triviality as a Q bundle means that in local patch, our Q can be separated in two pieces. First is just dx from the base, and some vertical part. And in this talk, we don't really care about global aspects. We always work in some patch. And we assume that globally, the whole gauge PD is just a product of two Q manifolds of base and fiber. And effectively, we'll talk about everything interesting happen in fiber. So usually we'll just talk about the fiber. And other thing about gauge PDs, we know that for field theories, you can describe the same gauge field theory in different sets of fields and symmetries. So a good example of this is the Cartan idea. So we can we can consider a Riemannian manifold, and Cartan showed that it can be equivalently described not in terms of metric, but in terms of Weyl-invariant and spin connection, subject to local SOD transformations. So it looks really different from the metric description, but they're equivalent, at least locally. And in the GHPD language, we can give the following definition of equivalence. So some sub-GPD, which is just sub-bundle, and Q is tangent to it, sub-GPD called an equivalent reduction if locally there exists set of functions W such that V equals to QW are independent, V and Q on W are independent, and this subbundle is zero locus of V and W. And these functions V and W called contractible pairs. And technically it simply means that you have some GHPD, you have some good coordinate system in which you see that action of Q on some coordinates is another coordinate. And then you can just put them to be zero, and by definition, it's equivalent GHPD. And we'll use it a lot. And for example, this Cartan description of Riemannian geometry can be obtained in this way in the GHPD language. So we can start with some GHPD for Riemannian geometry and then make this elimination of contractible pairs to get Cartan formulation. It's quite nice. And now I can say something about, in the beginning I told you that GHPD is objects that behave well when you restrict it to some boundary. And I tried to illustrate on this picture how it looks like. So on the left-hand side, we have our original GHPD, kind of field, and we see that we have some boundary on the base. Then we can just pull back our bundle to this boundary. So we simply forget about points inside. And this is, again, a GHPD, and it's a good definition of some boundary theory, and you will be interested in it in this talk. But also you see this blue line on the right-hand side. This is the following, because if you're talking about some physics or something, sometimes you want to add some additional boundary conditions, to impose some additional boundary conditions. And in this language, it means that you're considering some subbundle in your GPD on the boundary. But we will not discuss boundary conditions in this talk. Okay, I have finished the general part about GHPDs. And let me say something about GR and its asymptotic infinity. There are beautiful idea by Penrose how to conformally compactify Riemannian manifold. Suppose we have some manifold M and metric tensor which is defined only in the interior of M, and it diverges when we are going to the boundary. And we can say that this boundary is infinity for our metric defined only on the interior. But you can ask, like, is there some structure that metric, which is defined only in the interior, will still induce on the boundary? And to do this, to answer this question, you need to reformulate your system a bit. You can introduce additional field in your system, omega, with the following gauge transformation. And also you ask this omega to be a defining function for the boundary. So you're saying that zero locus of omega is your boundary. And because in the interior, omega is non-zero, and you have this gauge transformation, in the interior, you always can use this gauge transformation to put omega wherever you want. So for example, you can put omega to be 1 in the interior. And in the interior, it's just equivalent reformulation. You just added some field, which is completely fixed by gauge symmetry. But on the boundary, it's not like this. So you can define some new metric, just multiplying omega squared on original G tilde. And for this new metric, you have the following gauge transformation, which looks like, and it's really is, conformal Weyl transformation of metric. And it's which means that M is conformal. And if G extends smoothly to the boundary, which might happen because original G tilde diverges when you're going to the boundary, but omega squared is 0 there. So it might happen that your G will be well defined also on the boundary. And then if it happened, and it happened in gravity example, in most examples, you'll see that your M is now equipped with a conformal manifold structure. So metric structure, Riemannian structure up to Weyl transformation. And this structure is well defined on the whole M. So you had metric tensor only inside your manifold. Now you have conformal metric on the whole manifold and also this additional field omega defined there, but you have also an additional symmetry corresponding to lambda.
Field here, I mean omega, means vector field.
No, it's a scalar field. It's scalar field.
But what kind of an object is it? What is omega?
Omega is just a scalar field on your space.
Vector field? Oh, okay.
No, scalar.
Oh.
Yeah, and yeah. Okay. And yeah, now I can say how it looks like in this GHPD language. So our bundle is, as I said, I don't care about global aspects today. And I assume that my GHPD is just a direct product of T1x cross some fiber F. And from now on, we'll be interested only in F. And coordinates on F are the following. G is a coordinate corresponding to the metric tensor. And also we have infinite prolongations of it. So it's infinite amount of coordinates corresponding to G. And I like, for some reason, to write it not as coordinates, but like as action of total derivative on some G. It's quite useful for some reasons. So we have G, we have jets of G, also we have omega and jets of omega. And also, as usual in some BV-BRST prescription, we have additional coordinates of degree 1 correspond to symmetries that we have. So we have lambda of Gauss degree 1, and they are anti-commuting, and all jets of lambda. And also psi, which correspond to diffeomorphism transformations, and its jets. And omega equal or greater than 0. And the action of Q, now I'm just defining our first GHPD. So I can define Q in the following way. It's usual BRST prescription. What you need to do to define BRST differential, you need to take gauge transformation of your field and replace all of the parameters of your transformation with ghosts, with corresponding ghosts. So action of Q on G, what does it mean? First three terms is just a lead derivative of G, where I replaced parameter with this psi, correspond to diffeomorphism ghost. And last term just means that it's of weight 2 with respect to Weyl transformation. And for omega, first term simply means that it's a scalar field under diffeomorphisms. And second term says that it's of Weyl weight 1. And you can see that I already wrote this kind of formula on the previous slide. And for psi and lambda, it's just a lead derivative because they are anti-commuting. And we define Q on all of its jets, simply asking Q to be commuting with total derivative. But what I described before, it was kind of off-shell system. To talk about on-shell, we need to choose some equation manifold. And it will be useful for us because Einstein equations are quite nonlinear, and we don't know how to work with it in interior terms. We'll work with ideal which zero locus correspond to equation surface. And this ideal in this case is, I define it as total derivative prolongations of functions in Formula 1. And of course, you might ask me, and yeah, firstly, I need to say what are the what are the letters here? So gamma is Christoffel symbols constructed from jets of metric, and pi is Schouten tensor, which is trace modification of rich tensor. So it contains the same information. It's proportional to rich tensor plus some trace corrections. So it contains the same information, but it's quite useful to work with Schouten tensor in the conformal geometry setup. And pi without indices is just a trace of Schouten tensor. And lambda tilde here is just constant, depending on cosmological constant, but everything what we need here is just it's some non-zero constant, just some parameter. So you might ask me like why I'm saying that it corresponds to Einstein equations. It doesn't look like Einstein equations at all. But here's the trick. Because, as I said, we are trying to write Einstein equations in a non-usual set of fields. So what we need to check is that if we eliminate our omega, we'll get, for omega greater than 0, we'll get again Einstein equations. So the statement is that if omega is greater than 0, then logarithm of omega, which is a perfect function for omega greater than 0, and lambda form contractible pairs. And I can simply put omega to be 1 and lambda to be 0. And that what I'll see on what will happen with these functions. On the first line in Formula 1, only the last term will survive. And we'll see that trace-free part of Schouten tensor, and corresponding equation is trace-free part of Schouten tensor equals to 0. But as I said, Schouten tensor is a trace modification of rich tensor, so they have the same trace-free component. So it's just trace-free part of Einstein equations. And in the second equation, we see that only the last two terms survive, and it will simply say that trace of Ricci equals to some constant, and it is trace part of Einstein equation. So what we check that if omega is greater than 0, this system is equivalent to the usual Einstein equations, usual system for Einstein equations. But of course, we are not interested in the case omega greater than 0 because the main property of this system is that it's also well defined when omega equals to 0, which is a boundary for us. And but I can make another equivalent reduction because I can notice that part of my system is conformal geometry, and there exists some elimination of contractible pairs in conformal geometry sector. I'm not going to describe it in details because it's quite technical, too technical, but I can give you the answer. After this elimination, you have the following fiber coordinates. You have G without jets. You have omega, but also you have prolongations of omega, but not with total derivative. With another vector field, nabla. I'll say a bit more about it later, but here it's vector field defined on the surface, and it makes the work that usually total derivative do. So it generates coordinate system for you, like here. And also we have coordinate corresponding to the Weyl tensor. So this is just this double V is just some coordinate, which have the symmetries of the Weyl tensor. And Weyl tensor is a trace-free part of Riemann tensor. And also you have all of prolongations of your double V. This coordinate system is a bit overdetermined because we also have Bianchi identities for the Weyl tensor. And also we have the Gauss degree 1 sector, and after this reduction, it's finite dimensional. So there are no like multi-index here, it's just A, 1A. And yeah, nabla is defined in this way, is commutator of Q with partial derivative with respect to psi. And of course, it doesn't look too good because partial derivative is like you want to have some coordinate independence, but The good thing is that it's partial derivative with respect to Gauss degree 1 coordinate, and it does not depend on coordinate changes in Gauss degree 0 sector. And Gauss degree 1 sector is finite dimensional, and it's vector space and supervector space, and you can think about this as something like fixing basis in the algebra or something like this. So it's not too bad definition. And also you can pull back your ideal corresponding to Einstein equation to this reduction surface, and now it's generated. It's a small statement that is generated by nabla prolongations, not total derivative prolongations, of the following functions. And why I lost total derivative? Total derivative is simply not tangent to this surface. So we don't have total derivative here, but we have this nabla, which we are using to determine useful coordinate system, and also for prolonging the equations. And but it's not. You cannot really think about it as a total derivative because they are not commuting. You can calculate the commutator of two nablas, and it's proportional to this coordinate which correspond to the Weyl tensor. Here, delta and gamma are some vector fields. I don't want to describe it, but you see that commutator of these nablas is kind of proportional to the curvature, and you can think about this as something like covariant total derivative. I'm not sure about the terminology. And also you can ask what this nabla will induce on the solution space. So suppose we have some solution sigma, and you can ask it, we can use it to define some vector field along the section, simply just by commutation. And in examples, you'll see that it determines something known as Weyl covariant derivative on the space of solutions. This is Levi-Civita derivative plus additional Houghton tensor corrections. And it's quite useful in conformal geometry because you can write a lot of formulas in really short way, like without, like in one line instead of 5 lines, something like this. Now we are ready to go on a boundary. Our boundary is specified by 2 conditions. First condition is omega equals to 0, which, as I said before, just we're asking omega to be defining function for the boundary. But also we need to ask additional condition, q omega to be equal to 0. You can call it q boundary. We called it in the paper in some sense, but it's just because of this condition, q is tangent to this boundary, and because we are in this q manifold setup, we need to ask also for q omega to be 0. And we also ask some regularity nabla omega not 0. It's just some small regularity condition. Then we can again go to the equivalent GPD on the boundary. After some elimination of contractible pairs, we'll get some Q submanifold of the original F called FB. And here we didn't do anything. Like we had some offshore system, we pull it back to the boundary. We may, and from some moment we are considering this FB, which is equivalent to just a boundary GPD. But the good question is, we had ideal corresponding to Einstein equations in F, and usually I'll call F as a bulk. We had some ideal corresponding to Einstein equations in a bulk, and what is its pullback to the boundary? And technically, it's quite a hard question. You need to work a bit. And to explain it, I will split index on my original F as I just made some random splitting in 2 parts. Omega is just one index, and it's kind of normal index to the boundary. And big A is kind of tangent index to the boundary and have dimension d-1, where d is dimension of Bach. And for any function in the bulk, we can introduce the following notation, just this kind of normal derivative. It's just nabla A where we put it omega index inside. This normal derivative acting I times on H. It's just useful notation. And using this splitting, we can decompose Weyl coordinates corresponding to Weyl tensor with respect to this decomposition. Like if we had Weyl tensor coordinate corresponding to the Weyl tensor with small indices, can we put 3 omega indices inside? We cannot, because it's antisymmetric in pairs, like the Riemann tensor. But we can put 2 omega indices inside, and we call it T. Also, we can put 1 omega index inside and call it G. And we can decompose the whole this kind of covariant jet of the Weyl tensor in the following way. And you see that normal derivatives to the boundary are only in the last term, this M. We have them only there because we used Bianchi identities to put omega index inside of the Weyl tensor. Now I'm ready to formulate the proposition. Pullback of this ideal corresponding to general relativity on the boundary is generated by nabla A, where, is generated by nabla A, where A is kind of boundary index. Prolongations of function of the following functions on F pulled back to the boundary, GPDE. And of course, it doesn't look too good, like a lot of notations here, but let me just describe what these functions mean. If we think about them as an equation, first 3 of them, you can change coordinates in the way where this G omega omega and these guys will be just coordinates on your bundle and on your Q manifold on fiber. And you can, zero locus of this equation is just you saying that some coordinate equals to something. So it's not too not hard equation. With second line, we don't know yet. It's something strange. Some nabla omega acting a lot of times, or nabla B acting on some T. Okay, we don't have interpretation for now. I'll describe it later. And last equation. In the last equation, we have this numerical factor d minus 3 minus g on Tg. And Tg, you can also choose them as part of coordinate system. And if this numerical factor is non-zero, so g is not d minus 3, then you can think about this equation as again just equation on coordinate equations that's saying that some coordinate equals to something. But if j is d minus 3, we have something. We don't know what is the interpretation of it for now. And we can define some partially solved boundary system, which is just zero locus of these simple equations. So everything except second line and third line for g equals to d minus 3. So we solved part of Einstein equations induced on a boundary. And we call it f hat. And f hat. And we have this. And from now on, you can forget about f without hat. We will not use it. We denote the embedding of this f hat inside the bulk Q manifold F as b hat. And we also use the following notation: b hat pullback on any function on F is just h hat. And now interesting thing happened. Because vector fields nabla omega are ideologically they are normal to the boundary, of course, they are not tangent to f hat considered as a submanifold in F. But because of Einstein equations, a bit strange thing happened. the following vector fields, which are a joint action of nabla omega and times on nabla A, so it's just some iterated commutator, are tangent to f hat inside F. And that's happened precisely because we solved part of Einstein equations. This is the reason why they are tangent. And technically, it will give us the following formula. So if we saw it on the previous slide, we had some strange equations of this form, some nabla A, nabla big A, nabla omega in some power acting on it, and we want to pull it back to the boundary. And using the fact that these iterated commutators are tangent, this is just simple combinatorics that you can rewrite it as a formula defined on boundary itself. So D is tangent, it will give us also vector field on the boundary, which I call the same letter. And the right-hand side is defined on the boundary itself. So to compute left-hand side of this equation, sometimes you don't need to compute it in a bulk and then pull back on the boundary. You can pull back it on the boundary itself. And let me describe f hat in a bit more precise way. Induced fiber coordinates on f hat are the following. And I split them in two parts. So first part, as I'll show later, correspond to the leading data for gravity, or you can call it Dirichlet data. And second part correspond to the Neumann data for to the subleading data for gravity, and you can call it Neumann data. And here, this curly T is just TAB, D minus 3, and pull it back to the boundary. And TD minus 3 is precisely the 2 slides before, is precisely the equation. We solved the last line for everything except TD minus 3. So this is the one guy left. Here. And okay, I split it coordinates in some way, but because I'm working locally, I can split them whatever I want way. Like why I split them in this way? Because this splitting have a good property. It's preserved by the Q structure. So if we consider subalgebra of functions on our f hat generated by first subset, Q preserve these subalgebra of functions. And in geometrical way, it means that our f hat is itself bundle over some f hat conf. Sorry for a lot of letters. F hat conf have, and this bundle have fiber coordinates with this subleading data. And now, proposition. We can show that we can consider this f hat conf. We can go back to the whole GPD, which is like T1, which is boundary of our space-time multiplied on this fiber with this Q structure, and we can show that this f conf is equivalent as a gauge PDE to gauge PDE describing unconstrained conformal geometry on the boundary. So this f conf is kind of GPDE correspond to the unconstrained conformal geometry, and the whole gauge PDE f hat is describe conformal geometry together with some unconstrained field T that transforms non-trivially under Weyl transformations. And this f hat is, we can call it off-shell system. So it describes to us two unconstrained field, conformal metric and some additional, which is leading data for gravity, and additional T, which is subleading data for gravity. But it's off-shell. As I said, it's off-shell. But what is there? I mean, we obtained this Q manifold solving part of Einstein equations, but we also have something left. The pullback of ideal corresponding to general relativity to this f hat is generated by nabla A prolongations of the following functions. it's just rewriting of formulas that I wrote before when I wrote Einstein equations pulled back to the boundary, where I used this formula for curly D. And so we have some simple system. We have some GHPD which we interpret as off-shell system with some ideal which zero locus is kind of on-shell for a system. And yeah, so now the problem is that here on the right-hand side, we have some functions, we have some vector fields, some functions G and T, and some vector fields D, but yet we don't know how they're not the coordinates. Functions is J and T, they are not the coordinates. They are just some functions pulled back from the bulk, and how to write it in coordinates on the boundary. And it's a big technical question, because if you try to do it in a stupid way, just computing something in a bulk and pulling back to the boundary, it's insanely hard work. But now we can formulate the following theorem, which we call the boundary calculus, which is in the title of our work, of this talk. System of functions and vector field T, J, and D, which are exactly in these formulas both, they can be recursively determined in terms of functions pulled back from fconf. So in other terms, they do not depend on this subleading data for gravity. And this theorem is not too concrete because I don't want to demonstrate this recursive procedure in a talk, but the thing is that there are two statements, basically. The first is that it can be recursively determined on the boundary itself, so you don't need to pull back something from the bulk. You can compute them in terms of boundary. There's some iterative procedure going from low levels in N to high levels. And this iterative procedure is extremely efficient, what I'll show you later. You can construct really big things with this iterative procedure, and it's quite simple. And other statement in this theorem is that they're determined in terms of functions pulled back from fconf, so they do not depend, they depend only on leading data for gravity. And yeah, so corollary is that first, if we look at the first generator, we see that it does not depend, from this theorem, it follows that it does not depend on subleading data. So this is, if you interpret it as an equation, it's equation imposed only on conformal geometry sector. And the second equation, first term, of course, depend on subleading data, and it looks something like conservation law. But also you have some additional sum, and this sum depend only on conformal geometry sector. So you can interpret the second equation as conservation law plus additional corrections. And let me say a bit more about this. The first equation, which is O with two indices. Using this boundary calculus theorem, using this iterative procedure, you can show that this O can be written in this way. So B hat is what is known in conformal geometry setup as a Bach tensor. It's second divergence of Weyl tensor. Of course, strictly speaking, it's simple because we are working not on space of solutions, but on the Q manifold, on GHPD. And this equation is something like Bach tensor, a lot of Laplacian nabla acting on it, plus a lot of corrections. And for example, if dimension of bulk is 5, we see that it's just Bach tensor. And this fact is quite known in gravity. It's known that if you have asymptotically AdS gravity in a bulk, then on the boundary you'll have Bach flatness equation, which is equation for conformal gravity. So in some sense, yeah, okay. And also you can compute it for bulk dimension 7. It will look like here. And you see that there are more terms here. And really, if you try to compute it for higher dimensions, you'll see that number of terms in this differential in this equation, it grows kind of exponentially. You have in the next dimension, it will be operator on the one page, basically. And if dimension of boundary is odd, then it's automatically 0. So what I showed before, it was for even dimensional boundary. And this tensor is automatically, by construction, it's Weyl-invariant because we are working in this gauge with these gauge equations. By construction, everything will get on boundary because it's described conformal boundary, conformal manifold, it will be automatically conformally invariant. And this is a good way to obtain something conformally invariant, some conformally invariant differential operators on the boundary, because otherwise it's really hard to construct them just by scratch. You see that they are quite big, and yeah. And also I can say something about subleading data for gravity. As I showed, equation for it is something like conservation law plus additional corrections from conformal geometry sector. And you can show that there are some strange fact, which we saw that equations that I showed you before, obstruction equation, does not depend on the subleading data. You just simply don't see it. So it's conformally invariant by construction without any assumptions. But the ideal for GR, pulled back to the boundary, it's Q invariant only as a whole. Like I cannot. So the question is, like, is this equation on the subleading is invariant if we do not impose abstraction equation for the conformal background? And the answer is no. And even more, Weyl invariance of this conservation equation is equivalent to imposing the abstraction equation on the background. And it looks quite nice. And okay, it's at least me, I don't have good interpretation for it, but it looks interesting. And also you can see that this T, like solution corresponding to T, it's okay, but it was said badly, but single back T transform under Weyl transformation as a field of some weight, but also with some inhomogeneous terms, which proportional to the curvature of a background. So it's not, in terminology of, if someone know it, some CFT terminology, it's not primary field. It also have some additional inhomogeneous corrections in transformation. So okay, that's all for gravity. Do you have some questions? Because it's some point where you can ask that.
No question. Then please proceed.
Okay. Okay. And I'll briefly say something what happened if we have some additional gauge fields living on our background. I'll start with just usual, like not in gauge PD terms. So suppose we have some gauge field defined on a metric background, and we have some differential diffeomorphism invariant differential equation written on this phi tilde. Phi tilde here is not scalar field, it's anything, literally anything. It might be scalar field, Young-Mills field, some form or something, just really general consideration. You have diffeomorphism invariant differential equation written in terms of physical metric, which is ill-defined on the boundary. And we can rescale not only the metric tensor, but also this scalar field with some weight W. Here W is just real number. This W is a real number. And we can assume, so we had equation written in terms of phi tilde and G tilde, and we can rewrite it in the new set of fields. And let us assume that this equation will take the following form. Here, this term is, as you can see, is divergent when you go in to omega equals to 0. But we ask these terms to be well defined even when omega equals to 0. So we ask pk we ask that pk do not depend on omegas, but it might depend on derivatives of omega. And we can call p without tilde, which is just this regular part. We can call it conformal-like version of p tilde. And why it's a good definition? Because if we are in a bulk, there's no reason to choose p tilde or p because they describe the same, because we always can put omega to be 1. So it's kind of regularization of our original differential equation to the boundary, which is the same if we're talking about just about interior. And in GHPD language, field described on some background can be defined on some background can be described by Q bundle. So here I again wrote it in terms of fiber. So we had some FQ, and we define some Q bundle over it. And we already saw the example of such system. Our F hat was a bundle over F corresponding over conformal geometry part. So, and work for general case. And of course, if you have some solution of F, you can just restrict this F phi to this solution as manifold, and you get system described just phi on some background. And we, in the gravity sector, we constructed embedding of this useful F hat inside F. And because it's just a bundle, we can pull back F phi to the boundary, which describes the field on the background of the boundary theory. So the general receipt is quite simple. I'll be really brief about examples. So suppose this is procedure regularized the scalar field. We have the following, it described by the following fiber coordinates, which is just this covariant jet of phi. An action of Q is like here. And ideal corresponding to Klein-Gordon equation generated by Nabla prolongations of the following functions. It looks, again, it looks not like quite Klein-Gordon, but if we are in the interior, we can put omega to be 1. Only first term and the last term will survive. And we'll get the original Klein-Gordon equation. And in the action of Q, of course, lambda term will disappear if we are in the interior. Now we can pull back to the boundary. Also, for some reason, I want to fix mass of the field, but it's not necessary. And we obtain the following fiber coordinates, and the ideal of Klein-Gordon equations pulled back there is generated by the following functions. And here again, you see that this equation looks like equation that says that some coordinate phi n equals to something, but there are some factor which can be 0. This factor is defined here through the weight and dimension. And if C is equals to 0 for some n, then you get some non-trivial equation. And you have some subleading field which respond to this n. But if it's nowhere 0, then this equation simply just says that this coordinate equals, all the coordinates equal to something. Yeah. So for example, when C equals to 0 for some n, when weight is like here, it's simply just solution of equation C equals to 0. And we have the following equation imposed on a scalar field sector. It can be written using this boundary calculus theorem. It can be written as some power of Laplacian acting on a leading on the boundary. And subleading is unconstrained, but its Weyl transformations are non-trivial, include leading term. For example, if L is equal to 3, L is this parameter here, like some natural number. If L equals to 3, then we have the following equation. And we see that there are T2 here, which is if dimension of boundary is of bulk is 5, then it's D minus 3, then it's this equation includes subleading of gravity. So this is equation which defined not purely on a conformal geometry background. It also includes subleading of gravity. But if dimension of boundary is greater than 4, then then using boundary calculus theorem, we can see that T2 is just Bach tensor up to constant, and this equation becomes some famous GJMS equation known in literature. But this, again, this formalism is quite useful to find the explicit formulas for these operators. And also, Weyl transformation of the subleading field is quite big and strange. Another example, I can put weight to be 1 and boundary dimension to be odd. Then I have the following equation. It looks like Laplacian, but where we replaced metric with the subleading field for gravity. So it's quite strange. And one interpretation of this equation, we can ask it to be satisfied if for all subleadings of gravity, which will mean that because T is trace-free, it will mean that second derivative with this nabla, so phi is vanish. And this is the famous almost Einstein equation for phi. So we took Klein-Gordon field in the bulk on a background of GR. We pull it back to the boundary, and on the boundary, by some miracle, we again see Einstein equation, which came to us from Klein-Gordon field. Oh, okay. And yeah, really short about Young-Mills. It's known that there are some conformal-like version of Young-Mills equation. Again, if you put omega to be 0 of omega to be 1, it's just the Young-Mills equation. And here I'm using shorthand notation for F. It's algebraically valued curvature associated with A. So I don't write indices for the algebra. And on the boundary, again, it's long story short, will get the following equations on leading and subleading. So we have A, which is leading part, J, which is subleading. They are subject to, again, equations of similar form as for gravity. So here we have Maxwell equation and sub-Laplacian acting on it, plus corrections. And for subleading, we have some conservation equation, plus, again, some corrections. And I just want to demonstrate that how efficient this formalism is to calculate this stuff. In a case when boundary dimension is 8, we can calculate this equation for the leading field and rewrite it in terms of usual Levi-Civita connection on the boundary nabla G. And you see that this is a huge operator. Like here is Laplacian acting on the whole bracket. Here is some operator acting again. Okay, so it's really big differential operator. And again, of course, the main property of this equation, like why we are interested in this operator, because it's by construction conformally invariant, and it's really hard to construct Weyl-invariant differential operators. And you can think about this as conformally invariant generalization of Young-Mills in dimension 8. And of course, we are not really interested in this particular operator, but it's just a demonstration that you can construct such kind of things with this technique. And despite it looks too big and looks hard, with this boundary calculus theorem, with this iterative procedure, you can construct it in like hour. It took like hour or two to construct this guy. Okay, so conclusions. We presented some geometric and, despite I worked in coordinates, it's coordinate independent BV approach to the boundary structure of gravity, but at the level of equations of motion. If cosmological constant is non-zero, we constructed some efficient calculus for computing obstruction equations, which are conformally invariant by construction, and it's formulated in some good covariant derivatives automatically. And we can use this calculus to get some systematic methods for computing GJMS, high-Young mills, etc. And what I had not shown here is that for zero cosmological constant case, this approach you can use to obtain asymptotic symmetries, BMS group, and we wrote it in some article before. And also there's some work in progress. You can think about Lagrangian generalization of this picture, because again, this talk was about level of equations of motion. You can construct some efficient calculus for obtaining not only equations of motion, but also conformally invariant actions for obstruction equation. You can construct some BV version of covariant free space formalism to compute asymptotic charges. A lot of work to be done. Okay, thank you very much.
Thank you very much. Questions, remarks? No question as always, no remark. Okay, I have at least one question. One thing I don't understand, and maybe this means that I understand nothing. Well, in a lot of your formulas above, it was assumed that dimension is rather big, sometimes bigger than 3, sometimes bigger than 5, and so on. But what happens if we have, well, so to say, usual physical dimension? If the dimension equals 4, what happens?
For dimension 4, it at least everything worked good. Like, I should mention this before, that for the whole thing is one dimension of bulk 4 or greater. But for 4 it works, and
but formulas are different.
Not really. Like here, I mean, I think I said that dimension is something only on the Klein-Gordon case.
So, for example, well, sometimes
there will maybe
something to the power d minus 5.
It's
So what happens if d is?
You're right. You're right, but in this formula it's d minus 5.
Yeah, for example, here.
And I assume that this is for when boundary dimension is even. And if d equals to 4, then boundary dimension is odd, and we have O equals to 0. So for bulk dimension 4, it's usually it's kind of trivial. So it's, I mean, you have this leading and subleading, but you don't have non-trivial equations on leading.
Okay, thanks. Questions, remarks? Maxim, don't you want to comment? Maxim?
Yes, I'm here. Yeah. Well, I think Misha was quite clear with his talk.
Yes, I agree.
Yeah, regarding dimensions, you see, the thing is, so physical, one should, okay, it's difficult to say what is the right physical dimension in this context. The usual AdS CFT setup is when boundary dimension is 4. So bulk dimension is 5. In some sense. And then this story is well known, and then this equation is precisely Bach equation, which is known in physics as a conformal gravity equation of motion. Or if we go lower in dimensions, then things start to be not less interesting for us, not in principle, and simpler, because if we are if bulk is 4-dimensional, then there is no non-trivial equation on the boundary. But if bulk is 3-dimensional, then gravity is topological. This is a relatively simple situation, which is very well studied, because there are no degrees of freedom, so you don't need this kind of technique to analyze the situation, or at least it substantially simplifies. So this is more or less the relation with what people are interested in physics. Of course, all these questions in lower dimensions are well studied, but it turns out that once you go up with dimensions, things become very, very difficult technically, because there is plenty of conformal invariants, plenty of conformal invariant equations which are difficult to obtain. And maybe the message is that this technique surprisingly allows to really compute something in these difficult situations. For instance, this 8-dimensional Young-Mills equation that Mikhail has shown is apparently new. So people were not able to go further than 6 dimensions. And with this technique, it's relatively simple. It's not a crazy computation. So it looks like there is some good systematics behind. But speaking about physics, maybe the most interesting situation is nevertheless asymptotically flat, because it really corresponds to gravity in our because we are believed to live in more or less asymptotically flat space, 4-dimensional. But there, of course, technique is the same, like big picture is the same, but details are quite different, because it's a null infinity, and many things get modified. Hopefully, in some future, we will be able to explain how it works. Actually, we had a paper on, and I even gave a talk about a year ago about this approach to asymptotic symmetries. This was based on the paper which Mikhail, together with Mikhail, which he also showed. So it's possible to. It also turns out that it's a good technique to study asymptotic symmetries in asymptotically flat setups. The celebrated Bondi-Metzner-Sachs group, this BMS on the slide, you can see geometrically from in these terms, but of course still many things to be understood. So thank you.
And well, then the question, why it is reasonable to assume that the boundary is even dimensional? What are the physical reasons for this?
I think there are no there are no physical reasons. We don't really think about this asymptotically AdS gravity in this setup as like really physical manifold or something, and it's more way. I mean, it's more way to how to construct conformally invariant differential operator, something like this. And if we are talking about asymptotically AdS, for now, 4-dimensional case is really interesting. But for asymptotically AdS, yeah, we know basically everything for the 4 dimensions, and we can use these techniques to construct something for high dimensions.
May I add a little bit? So maybe in physics, what people are interested in is somehow the situation when boundary is 4-dimensional, and this corresponds to our 4-dimensional world. But but of course we are not conformal. We don't see our geometry is not conformal. It's rather Riemannian. But it turns out that at quantum level, it's interesting to study conformal quantum field theories, because they are simpler, and sometimes they give a good approximation to what's going on in general. And in particular, Young-Mills is classically, Young-Mills theory in 4 dimensions is conformally invariant. But this conformal invariance is classical and it is broken at quantum level, but still at tree level or in first approximation, it is almost conformal invariant. And so it can be approached by studying certain conformal versions of Young-Mills. But these are at the same time corresponds to geometry, gravity plus something in 5 dimensions. And this is what this whole story about holography and AdS CFT correspondence. That's why physicists for decades were interested in asymptotically anti-de Sitter spaces, because somehow they help to understand something about quantum field theory in 4 dimensions. But of course, all this is not so much literal because it requires some, let's say, it's approximate a little bit, like, because what we're interested in is not conformal, but AdS CFT describes conformal, and also in the bulk, according to the conjecture, it's not just 5-dimensional anti-de Sitter, but the 10-dimensional 5-dimensional anti-de Sitter times something compact, and that's where string theory is believed to live. But still, this geometry of asymptotically AdS space seem to capture some information about quantum field theory on the boundary. But of course, this what Misha was talking about is just geometrical techniques which can be used to study these physical situations in principle, but we limited ourselves to just let's say geometry. Thank you.
Okay. Well, thanks a lot again, both to Misha and Maxim. Misha, please send, if you do not object, of course, your slides either to me or to the seminar address. It doesn't matter. Okay, thanks a lot. So this is our last session this year. I wish everyone a Happy New Year, Merry Christmas, and hopefully we meet again in February.